Shall we? Thank you. Okay, good morning, everybody. Welcome to this Monday morning tutorial. Usually, the RIPE NCC Learning and Development Department gives out a tutorial on the first day. And the topic that we decided to talk about today would be RPKI validation, specifically the validation part. Now, before we start, a little bit of housekeeping. Basically, we will be covering three topics in large. I wasn't sure who the attendance will be, the level of knowledge with RPKI. So we decided to start with an RPKI refresher. We will not be spending a lot of time there, but basically what we would like to do is to define the problem statement. As an engineer, I was always taught that we have to ask the questions like, what are we trying to solve? What was the problem that existed before, etc. So we will define that, and then we will use this as a segue to introduce RPKI. So basically what it is, the components of the RPKI, we will see that there are two phases of it. One of them would be to protect your IP space by creating ROAs. So that would be the first part. And then the second part, where we'll spend a little bit more time, it would be the RPKI validation. And we will see what is needed over there in terms of additional software or servers that you'll need to have in your network, some of the deployment scenarios possible. And then we will talk a little bit about filtering with BGP origin validation. Now, we will end the tutorial with talking about some next steps related to BGP security. Now, I was told that I shouldn't walk a lot because the cameras are focused on me, but I'll try to do my best. I walk a lot, and I was told that I can be distracting. So if you get distracted, I'm sorry in advance, but I'm trying my best. All right, so let's start a little bit with the RPKI refresher, and then we'll jump to the meat of today's section. And typically, the reason why we needed RPKI is because BGP fundamentally, by default, by design, has some vulnerabilities. Now, these vulnerabilities have been identified for a very long time. They were talked, analyzed, etc. But a good reference would be RFC 4272, which defined basically three big categories of vulnerabilities related to BGP, right? And we have to understand one thing, that the early versions of BGP goes back to basically 1989, where in the cafeteria of an IETF meeting, there was an engineer from IBM and from Cisco, and they started sketching things on a couple of napkins. And that became what is known to be BGP. Now, you can imagine that back then, the internet landscapes, the network ecosystem was a little bit different than today. The people who are doing BGP, who are connecting the networks, they knew each other. I don't think that they really realized that at some point we would be having 80,000 autonomous systems like we have today, exchanging traffic on the internet, sometimes with people that you've never met before. So when BGP was being initially developed, it was based on trust. So I'm going to be peering with Andre in the back of the room. I know Andre. If something goes bad, I'll talk directly to him, etc. So there are no security mechanisms that were baked in the protocol itself, right? And because of that, there was no verification of the information. So what if Andre does a mistake? What if Andre starts lying to me and sends me bad information? So if we need to identify the three vectors of vulnerability, the first one would be that there's an absence of internal mechanisms to protect the exchange of the information. And when we say that, it means the integrity of the packets. So the packet that I'm receiving from my peer hasn't been tampered with. Has it been like a replay service behind that, etc.? For example, I cannot know if the source is authentic or not, and there's no encryption by default. So the packets are exchanged in clear text. So if there's somebody sitting in between, eavesdropping on the traffic, they can already get some sort of information about what is happening. Now, the second and probably one of the worst vulnerabilities is that within BGP itself, there are no mechanisms to validate the authority of a certain autonomous system to announce a certain IP address. So basically, on my BGP session, I can pretend to be whoever I want. I can start announcing whichever IP addresses from whatever AS that I want. And thirdly, that not only we cannot verify the authenticity of the origin, but also there are information in BGP related to the path. So it could be the AS path, like the series of autonomous system numbers that the announcement has went through, or there are other stuff related, maybe communities or other information related to the path itself. So BGP cannot verify these as well. And because of these vulnerabilities, if we start digging into each one of them, we'll find out that there are more and more technical reasons behind them. So for example, we already said BGP doesn't have integrity or confidentiality. It doesn't have any freshness service. So for example, let's say I'm eavesdropping on a BGP session. I get a copy of a BGP update message. So there's a certain route. And then let's say that in reality, that route has been withdrawn. I can wait a little bit of time, resend the BGP update message, and I can reinstall this route for malicious purposes or for denial of service purposes or whatever the case is. And of course, we've already said there are no encryption, there are no authentication, there's no integrity checks, etc. Now, no origin validation, again, it means that any AS can announce any prefix. So I could be announcing my IP addresses, and the next minute somebody in some places in the, I don't know, whatever, they start announcing my IP address. And lastly, that's the third vulnerability that we talked about. There's no authentication for the AS path. So instead of, if I would like to hijack traffic going towards a certain destination, instead of pretending that I am that destination, I can tell you, yeah, you know what? I'm directly connected to these guys. Send me your traffic. So also BGP cannot verify the AS path itself. So if we wanted to summarize these vulnerabilities, because of these, BGP is prone to different sorts of attacks. Because of the lack of freshness and integrity and all of this, the attacks can be done by exploiting the TCP stack itself or the BGP messages themselves. But practically, if we're targeting BGP, what happens is that we can hijack any IP prefix, all right? Or we can change the path. So this is what we talk about, prepending an AS path, modifying an AS path, etc. And things get worse because if there's something wrong happening between me and a certain neighbor, there is a very high probability that this information or misinformation or fake information will be spread on the internet, and then we start talking about regional outages or global outages. Now, we will be spending more time talking about origin hijacks because this is what RPKI is meant to stop at this point in time. And these are super quick to identify because theoretically, we know who is holding the IP addresses, the IP ranges. Theoretically, depending on like the benchmarks in BGPs, what have been done historically, the data and the databases, whether it's IRR or the RPKI system, we know who should be announcing certain prefixes, right? So a BGP origin hijack happens when somebody or some entity tries to impersonate another organization, and they start announcing their IP addresses, whether from the same autonomous system number or from a different autonomous system numbers. And typically, when we talk about hijacks, there are two types of hijacks that can happen. We talk about a prefix hijack or a sub-prefix hijack. Sorry. So in the prefix hijack, it happens when the adversary starts announcing the same prefix size, right? So let's say in this case, we have AS1 that originally announces a certain prefix, and the prefix size is /32. So typically, that would be the legitimate announcement, going in green. And then you have an adversary, let's call it the red one over here, AS5. and they start announcing the same prefix. All right. Now, what will happen in this case typically is that the effect of this malicious announcement, if it goes through, it wouldn't be a global outage. It would rather be more of probably a local outage or regional hijack. Why? Because you would have two competing announcements with two different AS paths, and then it would depend on the router, on the network receiving these announcements to decide which one is better. As we know, in BGP, there's the best path algorithm, and there are different rules to consider. It's not always the shortest AS path that wins, right? So that's why we're saying that it could be the case that some of the networks that are close to AS5, they will decide to send their traffic to AS5, but some of the networks that are closer to AS1, they might still decide to choose the legitimate path. And this is why we talk about not a global outage per se, but more of a local or localized outages. And now the second one is the sub-prefix hijack, and this is where things become a little bit trickier. So again, we have AS1 announcing a prefix P with a prefix size of /32, and then AS5, sorry for that, start announcing /48s. So now, if we are to reach this prefix, or at least the part of the prefix that is within the /48, networks around the world will have two options. Either use the route that leads to a /32 or use the route that leads to a /48. And at the end of the day, when it comes to routing, there's one golden rule, which is the longest prefix match. So in this scenario, this would be a global hijack because everybody in the world would start, sending their traffic to the adversary case. So RPKI was designed to address these sorts of issues, these hijacks. So the origin or the prefix hijack or the sub-prefix hijacks. Now, it's important to say that not all of these BGP incidents might be malicious, right? So it could be completely benign without any sort of global effects, or they can be just done by mistake, either like a root leak, a misconfiguration happening, a BGP optimizer going haywire, or just fat fingers and doing typos. As a network engineer myself, who touched a lot of networks back in the days, I'm too ashamed to admit how many times instead of 192, I typed 193. It happens, but when we work on the internet, these issues can become a little bit more tricky. So let's talk a little bit about RPKI and how it fixes these things. But before, I love the world of aviation. I know, for example, in the back of the room, Andre loves trains, I love planes. So let's book some flights, all right? So a couple of days ago, I was in Helsinki at a conference. So I live in Dubai myself. And I needed to book tickets going there. So I go to Emirates.com, I put my details there, and I come to the realization that in a couple of minutes, I will have to put my credit card information and pay a certain amount of money. So I wanted to make sure that this website is really legitimate, right? So that's really the airline's website. So what do? I click on that button a little bit to the top left, and it says, yeah, your connection is secure. So being the engineer that I am and the optimistic skeptical, I wanted to know, okay, why is it secure? So I click on the connection is secure, and it says it's secure because the certificate is valid. So I was like, all right, what is that certificate? Why is it valid? I click on it, and I'm presented with this information. And basically, this information says that, yeah, this website is really, Emirates.com. It belongs to the organization, which is Emirates Airlines, etc. And I go like, okay, but what does that mean? How can I make sure that this certificate is really good? What if these, these attackers, they forge a certain certificate? How can I make sure that this certificate is valid? So I started looking at the information. It says, okay, it's issued. You'll not be able to really see it here. Issued at the very top here to this website, to this organization. But then again, it says issued by, and it mentions here in this case DigiCert, one of the CAs, certificate authorities. Now, I might not trust the airline itself, but I trust the people or the organization who issued the certificate for them. And it's not only based like plain trust. There's some cryptographical information related to it. There's digital signatures. There's a public key. I can verify that the digital signature is correct. There's a validity period that says the certificate is valid between here and then, etc. And because I can verify the authenticity of the certificate, and because I trust the people who issued the certificate, then I trust this certificate, and thus I trust that this is the legitimate website. Now, why am I telling you all of this? Because RPKI does the same thing, but instead of certifying that this website is for this organization, it kind of verifies that certain IP addresses are to be announced by by a certain autonomous systems. So RPKI is a framework for securing the internet routing, right? And it allows us to verify cryptographically the association between resource holders and their resources. So in other terms, a resource holder, the entity or the person who has a certain range of IP addresses, they can decide who is going or what organization is going to be announcing these IP addresses. And in addition to this, it attaches digital certificates to these IP addresses and AS numbers. All right. And because of this, if we have these associations between IPs and ASNs and digital certificates, etc., later on in BGP, we can leverage this information to do what is called a BGP origin validation, BGP OV. All right. So it would allow us to answer questions such as, if I'm receiving BGP messages from Andre in the back in the room, I can say, is this correct? Is this by mistake? Does it conflict with other information, etc.? All right. So typically, RPKI, and to be clear from the very beginning, is not a silver bullet for all BGP issues, at least at the very moment. So what RPKI will be doing, again, until this point, it verifies the authenticity of the AS that should be originating IP addresses. It does not validate the path. So if I start telling you that, hey, I have the IP addresses of the RIPE NCC, and I start announcing them, you can verify this information or not. But if I tell you that, hey, you know what, I'm connected to the RIPE NCC, yes, send me your traffic, you cannot verify this. Well, we'll see at the very end that there are some solutions to this, but we'll talk about this at the very end. Now, how does the whole process work? From having these statements, authorized statements that says this AS will announce this IP, up to the point where networks can verify BGP announcements based on this information. So typically, this diagram encapsulates everything that happens with an RPKI. And basically, there are two parts that I would like to draw your attention to. The first part in black here, this is what we call the RPKI signing part. So let's say I'm an organization here, and I have a certain prefix Y. Okay, it could be IPv4, it can be IPv6, etc. It is up to me, the resource holder, to create some sort of a statement that says, this ASN will be announcing my prefix Y. In this case, I chose ASN 300 to be announcing my IP addresses. Now, ASN 300, it can be one of my autonomous system numbers. It can be the ASN of my upstream provider. It can be, I don't know, DDoS scrubbing service, whatever the case is, right? But you might tell me that, yeah, we already have mechanisms in place, like the root objects or the root 6 objects that specify something similar to this, right? But what RPKI introduces specifically is that you will be able to sign, to cryptographically sign these statements, and that's why we use the key here. And then you'll have a digital signature attached to this statement, right? Now, this authorized statement is what we call a ROA, a root origin authorization. And then we are going to publish these digitally signed statement in what we call a set of RPKI repositories. And we'll see later on some of these. So this is up until this point, we call this the RPKI signing. Now, who uses this information? I don't use it. I don't need to use it, right? It is for the other networks who will be receiving BGP announcements later on related to my IP addresses to prefix Y. They can revert back to these RPKI repositories, get these authorized statements, and verify if the information they are receiving regarding my prefixes are correct or not. So let's look at this scenario where AS300 starts announcing my prefix, Y, all right? They announce it in the wild. And it happened to be that they are pairing with AS200. Now AS200 is receiving a BGP announcement saying, yeah, AS300 are originating AS3000. Now, is this a legitimate information? How do we verify this? Typically, back in the days, we might have some prefix list, or AS path list. We go to the IRR data, we go to other information, etc. But now what AS200 can do is that it downloads the information, the validated, or let's say the digitally signed statements from the RPKI repositories, and then they can verify both information, what they receive in BGP and what is available in the RPKI repositories. And then based on this comparison, either they decide to keep the announcement, to drop the announcement, or to do a certain sort of treatment on that announcement. All right? So RPKI, in order to really benefit of it, there are two sides of it, two sides of the same coin. The first side is to actually create these statements. That's the black part. So everybody creates statements for their own IP addresses so that the other side, so the other networks, and that's the orange part, can verify the BGP announcements or the BGP information related to our own IP addresses. So the more networks create statements, the better it is for everybody to be sure that the BGP information that they are validating is actually correct. And towards the end of the second part, we'll see some statistics related to either or, the black part and the orange part. Now, just like when I showed you the case of the web certificate, we had at some point a source of trust. We call them the certificate authorities, because I trust DigiCert, because I trust VeriSign, then I trust this certificate, then I trust this website. And RPKI, there should be a source of trust, right? And these source of trust, we call them the trust anchors, and they happen to be 5, which are the 5 RARs. So you have the RIPE NCC, you have ARIN, you have LACNIC, you have AFRINIC, and you have APNIC. And the choice of these trust anchors is interesting because we are the organizations who allocate the IP addresses. So within our region, we know who we allocate the IP addresses to. In other terms, when somebody tries to create these digitally signed statements for these IP addresses, we can only restrict this to the legitimate resource holders. In the IRR world, the Internet Routing Registry, where we used to create the root and the root 6 objects, you know, it wasn't only one set of database. There was maybe 20, 23 databases at some point in time. Some of them are managed by RARs, but some others are either commercially run or run based on volunteering work, where basically anyone can go and create root objects for any IP addresses. In our case, in the case of RPKI, so if there's a member of the RIPE NCC that received a certain allocation of IPv4 or IPv6, only them are allowed to create these statements. So if we go back to this example over here, even though AS300 is going to announce prefix Y on the internet in BGP, they cannot create these ROAs for prefix Y. It is only the holders of prefix Y, so that organization at the top left, who are eligible to create these statements. So this, how can I say, it induces a certain level of trust that typically what you find in the RPKI repositories reflects what the holders of these IP addresses want. Now, whether it is updated or not, whether they were created correctly or not, that's a different stories. So just like in the previous case of the web certificate, you have DigiCert who issued the certificate. Just again, in RPKI, you'll have, for example, the RIPE NCC issuing a certificate for our members. So the member will have an LAR certificate, and then they can use this information to create the ROAs, etc. Now, there's a different deployment scenario where the member can issue their own certificate, and then we have it signed by the RIPE NCC, but that's a different story. Now, the chain of trust is very similar to what we can see in a web certificate as well. It all starts with the root certificate. That's the orange one. This is the root certificate of, let's say, the RIPE NCC or ARIN or the other RARs. It contains the public key of the RIPE NCC, us, and it is digitally signed. Now, how do we sign it? We sign it with our private key. You'll never have access to our private key. All right, so we sign it ourselves, so it's a self-signed certificate. Now, the LAR, and LAR is the member of the RIPE NCC, they get their LAR certificate. This LAR certificate will contain 3 pieces of information. First, it will contain the LAR resources, so that's IPv4, IPv6, and autonomous system numbers, right? It will contain the public key of the LAR, and it will be digitally signed. Now, who signs the certificate of the LAR? It will be signed by the root's private key. So in our case, the RIPE NCC will use our own private key to sign it. And then once the LAR has the blue certificate, they can start creating the ROAs that says this autonomous system will be announcing these IP address, and there's one more piece of information there. And the LAR will use their private keys to sign the ROA. So that's the chain of trust. Why am I letting you know this? Why am I stressing on this? Because later on, when we talk about the validation, we will see that the validation starts like from the reverse. We start from the ROA and we verify the chain of trust. Now, as we talked in the previous diagram, RPKI has 2 elements. The first part is the signing part, which is creating the ROAs for our prefixes and then publishing them in the RPKI repositories. And then the second part would be the validation, and we will be spending some time there. Now, before I start talking about the validation, I'd like to talk a little bit about the ROAs, because this is the beating heart of RPKI. If we don't have ROAs, enough ROAs and good quality ROAs, then we cannot do proper validation in the second step. And if we cannot do proper validation, we cannot do origin validation, and then the whole idea of RPKI crumbles. So the ROA, it's an authorized statement created by the resource holder, and practically it states 3 things: that a certain prefix will be announced by a certain ASN number, whether it is their own ASN number or someone else's, right? And it contains a 3rd piece of information, which is called the maximum length. We'll see it in a second, right? Now, it's important to understand and to know that we can have multiple ROAs for the same prefix. So let's say I have a certain prefix, I'm announcing it, but at some point, maybe another autonomous system will announce it again as well, let's say in the context of DDoS mitigation service, or in the case of an Anycast deployment, or whatever the case is. So I can have two ROAs, one with my ASN and another ROA with another ASN, both stating that they will be announcing the same IP prefixes. Or we can have overlapping ROAs. So for example, I can say, if we're talking about the IPv4 world, I can have a ROA for /22, saying it will be announced by a certain AS number, and I can have ROAs for a /48, for /24. If we're talking about IPv6, I can have a ROA for the /32 or /29 that I received from the RIPE NCC. And then if I announce /48s, I can also have ROAs for the /48s or what have you. Now, the three elements of ROA, and basically it's very simple, but I'm reiterating them because there's a reason why, and I'll get to it when we talk about the third component. The first one, the most obvious one, is the prefix. So which prefix I would like to authorize? In that case, it would be the 2001 DB8/48. That's the documentation prefix. Then we have the origin ASN. So this is where we specify one AS number that will be originating this /48. And the third one is maximum length. So that specifies up to what length I would like that AS to authorize that AS to announce. So to really understand it, I'll give a couple of examples. And I decided to keep these in this tutorial because for the last 2 years, I've been personally engaged in a lot of work with operators and regulators in certain parts of our service region in order to drive the RPKI adoption, whether from the signing part or from the validation part. And I see sometimes there are some issues, even within big operators, with the maximum length. I'll give a concrete example in a couple of seconds. So let's say that the RIPE NCC has a certain allocation, this /21, and we want it to be announced by AS 3333. So the RIPE NCC creates this specific ROA that says 193.00/21 with a maximum length of /22 will be originated by ASN AS 3333. Now, what this ROA says specifically that if the RIPE NCC AS 3333 announces the /21s or announces /22s, these will be valid according to this ROA. But if we start announcing the /23s or the /24s, then according to this specific ROA, there's something that is not correct. Now, there's absolutely no issue to have an additional ROA specifically for this /23 or specifically for this /24 or whatever the case is, right? Now, you can tell me, all right, why don't we create a ROA for the /21 with a maximum length of a /24? So basically, everything would be valid. Now, while that is true, everything would be valid, but that creates a security caveat where, let's say, you're not announcing this /24, but you have a ROA that validates everything. An attacker can start announcing this /24 using AF 3333, and then suddenly their announcement would be legitimate as per the ROA. So that's why the recommendation out there is to create through the ROAs in the RPKI system exactly what you do in BGP. All right, so if you have statements, if you have announcement for /21s only, then create ROAs only for /21s. And most of the invalid states that I've been seeing lately have to do with a maximum length mismatch. One of the latest cases that I was dealing with, and that was a couple of weeks ago, it was for a huge operator in the Middle East. They created ROAs for all of their space globally. It was everything was valid, but they have specific announcements that they do with some of their cloud providers and like the big cloud providers. And these announcements had a different size. So let's say the prefix was /22, but they announced /24s with their cloud providers, and these BGP announcements were being marked as invalid. Now, I see the same thing happening with other operators, with other entities. So please make sure that the maximum length is set to the correct value. My recommendation, the industry's recommendation, is whatever you do in BGP, you reflect it in the RPKI system. All right. Any questions so far? Okay. Now, did everybody here created ROAs before, or have been, exposed to ROAs, the RPKI dashboard, or not? The process is very simple. I'll do a very live demo. So typically, if you have access to your LAR portal, so if you're an LAR with the RIPE NCC and you have access to your portal, at the very bottom left, you'll see something called RPKI dashboard, right? And you click on it, and you will be brought to this specific dashboard. Now, typically, there are two major pieces of information that you see here. Oh, and by the way, you will only see this dashboard if you already started your RPKI journey. So first you ask for your certificate, you will be presented with certain terms and agreements, and then you can specify which mode that you would like, hosted or delegated. Let's say that you went with hosted, which is probably 99% of the cases so far. You'll end up with this dashboard. Now, there are two pieces of information here. The first one is BGP announcements, and that's basically our routing information service. So we have route collectors spread a little bit around the world, we do peers with a lot of other routers around there, and we see what is happening in BGP. So if there's any activity related to your IP addresses or your ASN numbers, you can see them here. So typically, there are currently 2 BGP announcements out there in the wild that have to do with our resources. Now, what are the resources that I'm talking about? You see here, there's this gray button called 3 certified resources. And if I click on it, it says that the resources that I have that are associated with my LER, this is AS2121, I have a /21, and I have a /48. Andre, correct me if I'm wrong, but these are the addresses used for the RIPE meetings, right? So currently, we are all using these IP addresses over here. Now, why is this important? Because if I try to create any ROA not related to this /21 or this /48, the system would lock me out. It wouldn't allow me to do it, right? But because these resources are within my certificate, my LAR certificate, that means only I can create statements for these, right? So this is what I see here, BGP announcements, and what is the status of them? They are valid. Why are they valid? Well, because I already have ROAs that say, all right, this announcement will be valid, and they are authorized. Now, let's say that I didn't have ROAs, so I'll go to the ROA section, and I'm going to delete them. I'm making sure that I'm in the pilot environment so that I don't break anything. Let's go here. Where's delete ROA? I delete the ROAs. I need to review, publish the changes, apply the changes. All right. So now, if I've never touched the RPKI dashboard, if I never had ROAs before, I'll be presented with something like this. I'd have 2 BGP announcements in the wild, and the situation for it, the validation status would be unknown. Why? Because there are no ROAs that say this /21 or this /48 should be announced by this ASN number. Now, to change this, you can either create the ROAs manually, so you click on a new ROA and you try to put the ASN number in the prefix, or because we love you and we want to make your life easier, we present you with a wizard. So you can just select the statements, the BGP announcements that we see on the internet, and then you click on create ROAs for selected BGP announcements. And then before we publish any change, you'll have to review it and say, okay, I approve it. So you click on the blue button over here and it says, all right, the change that we're proposing is that we are staging two ROAs. That's the first one over here, and that's the second one. Now, to the right side, it tells you what is the effect of these announcements. All right, so the effect is that these BGP announcements will go from unknown to a valid state. So yeah, I like green is a good thing. So I click on apply the changes and suddenly I have the status to valid. So either I can do this through the wizard, or let's say there's a certain prefix range that I haven't announced in BGP yet. So you will not be seeing it on the first screen, but still you would like to create ROAs for that. So very simply, I click on new ROA. I say, you know what? I want it to be announced by AS3333. And let's say I would like to be announcing /22, and the maximum prefix lengths to certify. Okay. No. I'm sorry. 193. Okay. And let's say, you know what, AI33 is going to announce the /22s and the /23s, so I want the maximum lengths to be /23, and that's it. I don't have to do anything else. Now, if I decided instead of 193, I want to create, I don't know, for 194, it would give me an error saying that prefix must belong to your certified resources again, which I have here, and then it wouldn't allow me to create it. All right, so basically this is how we can create ROAs and the trust, how the trust can be enforced within the RPKI system. Any questions so far? No? Yes? Maybe? Oh, sorry. All right, so now we get to the second part, which is the validation, right? Because everything we've done so far is nice, is cute, but if we don't start doing validation, as in deciding what to do with live BGP announcements based on the information in the RPKI system, then we haven't done really anything. All right, so validation is to verify the information provided by others. First, there are two steps for the validation to happen. The first thing is to validate that the data in the RPKI system is valid. Going back to the web certificate example that I gave, there are things that I looked at, like who was it issued from, the validity period, the public key, the digital signature, etc. So we need to do the same thing when it comes to these ROAs. Is the information inside them okay? Who created them? Are they eligible to create them? Is the validity period of the keys correct, etc.? And to be able to do this, we need to install a validator software, or what is sorry about that, or what is known in the industry as a relying party software. It should be within your network. And this software will validate the holdership through the public key and certificate infrastructure. So it downloads the ROAs, it looks at the whole thing, who signed them, etc. We'll see this in a second. Now, once that validator software comes back to you and tells you, okay, this is the final list of the validated ROAs, we call them VRPs later on, you can start taking this as a source of information against which you can compare the BGP announcements that you receive from your peers. And then you can compare the information and decide. You'll have three options. Either the information match, and that's a good thing. Either there's information mismatches, and that's a bad thing. Or it could be the case where, let's say, again, I'm peering with Andre. Andre sends me something, but I don't find information related to these IP addresses in the ROAs. So that's the third scenario. Now let's talk a little bit about the operations of these validator softwares, which again, they are known as relying party software. Basically, what they do is that they connect to the RPKI repositories using one of two protocols, either the rsync protocol, and that was the older one, or the RRDP protocol based on HTTPS. And the way it does is that the validator will have something called a TAL, Trust Anchor Locator, right? You remember we said earlier that the trust in the RPKI system is based on the 5 RARs, which are called the trust anchors. So the RIPE NCC, blah, 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 etc. So the validator, they should have access to these 5 trust anchors. Now, one way is to have the root certificates of the 5 RARs already embedded inside the validator. But it could be the case that the information inside the certificates, the root certificates, they change due to transfer of resources, etc. So instead of keep changing the root certificates and distributing them to the validators, what the validator will have is actually a pointer, URI pointer, to where it can find the root certificates and the public keys and so on. So the validator will look at the TALs, it will see the location of the 5 trust anchors, it will go connect to them, see where the RPKI repositories are, and then the next step would be to start downloading these ROAs either through rsync or through RRDP. So it downloads the ROAs from the different repositories, either the repositories of the trust anchors or the external repositories, and we'll see some of these in a second when we do a live walkthrough. And then it will validate the chain of trust. So you remember previously we had this, we saw this, we started with the root certificate, and then we said the private key is used to sign the LAR certificate, and then the LAR certificate would use their own private key to sign the ROA. Well, the validator starts from the other way around. It goes bottom up. So it will look at the ROA. Okay. It will look at the digital signature of the ROA. Now that ROA is signed by the LAR certificate. All right, let's look at the public key of the LAR certificate and see if it matches the digital signature of the ROA. So we'll use this public key, check the digital signature, and if it matches, we will say, okay, that ROA was created, was signed by this LAR. So let's look at the information inside the ROA, because the ROA has IP addresses and a yes number, right? So is the IP address inside the ROA included in the certificate and the resources of that certificate? If the answer is yes, then now we have 2 pieces of information. We have first that this ROA was really created by that LAR, and that LAR is the, let's say, legal holder of these resources. Now, I need to verify that these LAR certificates are also correct, because what if I inject malicious certificates? So I look at the digital signature of that LAR. All right, who signed it? It should be signed by the root certificate or by another parent LAR, if that's the case. But in this case, it is signed by the root certificate. So I look at the public key of the root certificate. I use it to check it against the digital signature of the LAR certificate. And if they match, then I would say, all right, this LAR certificate has been really signed by the root certificate. Now, how do I make sure that the root certificate is valid? Well, it's self-signed. And this is my source of trust. That's my trust anchor. So now what happens is that because I trust the orange certificate, I trust the LAR certificate, and then I trust the ROA. So the validator does this for every single ROA out there. And it would come up with an answer. If the chain of validation is okay, then the ROA is valid. We're not talking about the information inside the ROA. We're just saying that the ROA is validly accepted. Now, if something is broken, either the resources don't match between the ROA and the LAR certificate, or the validity of the keys being used to the signature is not it expired, or some of the digital signatures, they don't match, then that ROA, specific ROA, will be marked as invalid. Now, There are different RPKI validator options out there. You need to have the software in order to do all of this for you. Now, some of the most famous ones out there are the Routinator. They are built and managed by NLNet Labs. There's RPKI Client. It's part of the OpenBSD distribution. You have Port, which is another open source RPKI validator. There are a few others out there. So you can find some of the information over here. There's a more elaborate documentation on rpkireadthedocs.io. I would really invite you to take a look at there. If I was giving this session maybe 6 months ago, you'd find a fourth one. We had a fourth one on the slide, and that was the Octo RPKI from Cloudflare, but that was discontinued back in February. So why am I telling you this? I'm telling you this to always keep an eye on what is available out there, which distribution, which version is being available, is it maintained or not. Now, how do you choose which one? I always get this question, especially when we're doing our engagements with the regulators or the operators or the entities that want to start the RPKI. Which one do I choose? Do I go to Routinator? Do I go for the RPKI client, etc.? Well, you really need to evaluate the available validator softwares inside your network. What might work for you might not work for someone else, depending on the hardware you have, depending on the network requirements that you have, etc. So that's another thing to look at. Each validator might come with a specific hardware requirement, or let's say it says it's only supported on this distribution, that implementation, or that stack, or whatever. So check the hardware, check the software requirements, check the development language that it was developed with. It could be the case that you might need to do some tweaking. All of them almost work out of the box, but it could be that you want to change something. You can play around with the APIs, etc. So if you're familiar with the language, that would make your life easier. Check whether it is maintained or not. So, for example, the RIPE NCC back in days, we had the first validator for the community. It was called the RPKI validator, I think, or the RIPE validator, but that was discontinued a few years back. So if you're still using it, don't. I'm pretty sure that it shouldn't be out there anymore. Check whether there is an active community behind it. So if this is important for you, if you want to make sure that what you're deploying in your network right now has enough support out there, that it will be maintained for the next few years. So that's typically a good indicator if you have an active community behind it. And usually I wouldn't include this, but check if you can have potential support options. So you know how they always tell you free is better? Recently, I came to understand that this might not be the case. So I was engaging with different operators in the Middle East region, and we were trying to drive the RPKI adoption. We've done the ROA part. We moved countries from 2% of ROA space covered to 98%, so everything was great. And then we moved to stage 2, which is the validation. And we were like, okay, so these are the softwares available. These are the different options. There was even a presentation at one of the RIPE meetings. I think it was the one in Belgrade in RIPE 85, where a member of the community gave a presentation called an opinionated review of the validators available. So it was talking about the pros and cons of each validator. And then we did different workshops with them. We set milestones, and then suddenly I received some sort of a weird email saying, we cannot deploy the validators in our network. We would like to pay for someone for support if something happens. So for them, it was important that according to their compliance policies, they cannot install any piece of software inside their network if they don't have proper 24/7 support over it. So if this is something that is of importance to you, you can check for potential support options. Even though all of the RPKI softwares out there today, they are open source by nature, so you can download them and install them, run them for free. Some of the organizations behind them might offer you some sort of a support contract. Like, is it 9 to 5, 24/7? It depends. Now, which one to choose? This is a compilation that I've taken 2 days ago from RPKI Read the Docs. It shows you the different available validators so far, who is maintaining them, the language in which they were developed, and when was the last commit done on them. So for example, if you look at the Octo RPKI, you see that the last commit on their GitHub repository was in February. And basically that was to tell everybody that, hey, this will be discontinued from now on, and you should be using, for example, RPKI client. But if you take a look at something like Fort Validator, which was, the last commit was on 17th of May, or if you take a look at Routinator, which was in May, or RPKI client, which was in April, you see that these are pieces of softwares that are still relatively being maintained, actively developed. If there are some bugs or patches, security patches that need to be installed, they are available. So you might need to choose. Now, when deploying RPKI validators, you have to think about redundancy. I keep saying this again, that I blame my engineering training here. Always think about redundancy. So think about having at least 2 validators, all right? And preferably they should be in different locations. So different VLANs, even if it's within the same location, preferably in 2 different VLANs, 2 different networks, because if something happens on one of the VLANs, then it wouldn't affect both validators at the same time. And preferably, it could be from 2 different providers. So it could be, for example, you have one Fort and one Routinator, which is, for example, the combination that we do in one of our training courses, or it could be, one Routinator and one RPKI client, whatever the case is. Why? Because from a security perspective or an operational perspective, what if there was a bug on a certain distribution? If you had, for example, 2 Forts or 2 Routinators or 2 RPKI client, what might affect, like one validator will be affecting the second. But if you had 2 different validator from 2 different providers, chances are if you have a bug on one, the second would still be working just fine. I remember, I think, back in the early days when at the RIPE NCC, we had our own validator. We had some issues with the memory usage on these validators. So if that was the case where we hit, I don't know, a memory buffer overflow and something crashes, you'd still have another validator from another provider that would be, up and running. All right, so now you have the validator. It validated all the ROAs, and this is what we refer to as the validated cache. That would be the white thingy over here. Now, what happens? The whole idea is that we want our edge routers that are doing the eBGP sessions to be able to compare the information in BGP to the information in RPKI. So in a way, we need to get the validated caches that the validator produced all the way to the router. And this is where RPKI RTR comes in place. So we need to have the RTR protocol supported on the router. RTR stands RPKI to router. All right. So the validator will be, it will push, or most probably the more accurate description is that the router will go connect to the validator and pull the validated cache using the RTR protocol. Now, there are some different deployment scenarios here. Let's imagine that you have a big distributed network, all right? So you have edge routers in 20 different locations in different countries doing eBGP sessions, and you need to do some sort of BGP filtering there. Now, what are you going to do? Are you going to have a validator in each of these 20 different locations? So a validator software server sitting next to your router. It could be the case, or it can be the case where you say, I will have my validator sitting in a centralized data center, right? And then you can say, all right, no issue. I have my 20 routers in 20 different countries connecting through the RTR protocol to my centralized validator softwares, which are in my data center. It is possible, but what happens if the connection with this data center stops? Then in this case, we might lose access to the validated caches and the validated ROAs and so on. So there is a deployment scenario where you can use some sort of an RTR proxy. All right. So you'll have your validators sitting centrally in a data center, let's say, and then you'll have these RTR server proxies sitting closer to the edge, closer to where the routers are. Now, this RTR server can ingest data from different validators. So it can take data from one validator, two validators, three validators, whatever the case is, right? And it allows for different multiple deployment architectures. So the RTR can be per edge site, it can be closer, it can be in a CDN environment to distribute it better. It can support different deployment architecture, right? And typically we see this when we decide that we would like to have the validators centrally, and then we would like to have these validated cache closer to the edge in a decentralized manner. Now, there are different available softwares out there. There's one from Cloudflare called GoRTR, but that was also discontinued in February. We have one from BGP maintainer. There's one from the NLNet Labs, and there's one from Darren O'Connor. I think the one that is being mostly updated is the one from NLNet Labs, and that's called RTR. And basically, some of the things that you can do with these RTR servers is that you can ingest the data and then you can make it available through different formats like JSONs or CSV or whatever. So you can have your routers, for example, if the router doesn't talk RTR, it can probably ingest the data through JSON format, and then you'll have the validated caches out there. Okay. Now we'll do some sort of a live demo where we run a validator and we connect a router to it. Now I'll show you two examples. I have snapshots to make things a little bit faster and to have more time for questions later on. We will see the case of a Fort validator if we're running it, and then we'll see the case of a Routinator, and then we'll do in a live demo using our lab. I'll show you how to connect a router to it. It's basically super easy. Now, I will not go through the whole process of installing the validators. We will suppose that at this point in time, you have installed the validator software. So you can refer to the documentation of the maintainer about how you install it. Usually it's a few lines, command lines, and you install it. Now, in the case of the Fort, what you will need to do at the very beginning is to initialize the validator service, and you do that through the command fort --init tals. And the thing is, either you can leave it by default like this, or you can specify where your tals are, where your trust anchor locators are. So we do this in our lab, for example. What you see here is because we don't want the lab deployment to connect to the real trust anchor, so we point it towards, a test environment to make things faster. Why am I telling you this? Is because if you're running it in a test environment and you would like to focus on one specific TEL, you can use this parameter to tweak the surface, like point your validator towards the TEL that you want. And then later on, you enable the Fort service using the command enable now Fort, blah, blah, blah. And then you wait and you wait a little bit. You check if it's running. So you use SS command to check the statistics on the socket itself. And typically, if it's running, you'll have something like this. By default, Fort will be listening to port 323. And then if you'd like, you can check the logs to see where is the service in terms of initialization. Is it up and running? Did it connect to the tells? Did it download the ROAs? Did it validate the ROAs, etc.? Why it might be important? Because by default on that specific versions, on Fort you cannot connect to the validator unless the first cycle of validation finished. So basically, the validator should be up and running, connect to the tells, download the ROAs, verify all the ROAs are correct for the first time, and then we can start connecting the routers towards it. All right, so this is where you see in green that the first validation cycle has begun. Wait until the next notification to connect your routers. It says that it downloaded 200 valid ROAs, and then it says the validation cycle successfully ended. Now you can connect your routers. Now this behavior might change in the future or in different distributions or future versions of Fort. So always refer to the version that you're installing. Now, if you'd like to check the validated caches, so you're wondering, do I have a validated ROA for my /32? So what you can do, you grab your CIDR command for a specific 2001FF01/32, and then if it spits back an answer, a line saying, yeah, I saw a ROA that says AS101 will be announcing this /32 and the maximum prefix /32. What that means is that your validator found a ROA and it was able to validate it. So the chain of trust is completed. Now, if we're running a routinator, and again, that was specific to the version that we had in our lab, so things might have changed later on. So the service is initialized by default, so you don't have to initialize it like the other one, like Fort. So you enable it. We use the systemctl enable command. And then to check if it's running, we don't need to look at the socket statistics to see if it's listening. We just look at the processes. And we do a grep for the routinator process. So we can also use the curl command to check if the status. So it comes with an embedded browser, which you can hit up certain functions, in this case, the status command, and it would spit back a certain answer. So it says, yeah, this is the last update that we have. That's the version of the routinator that we have. In our case, we're using the RIPE-NCC pilot tel. So you see that was the specific trust anchor locator that we used, because otherwise it would be downloading hundreds of thousands of ROAs, and it would take a long while to have the lab running. And then it would tell you the final VRPs. These are the validated ROA payloads, blah, 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 etc. And also we can check if we have a certain specific validated ROA. How? Also, we can use the curl command to hit the HTTP function, and then we look for /21, and it will tell you, yes, I found it. I have an AS2121 who will be announcing this /21 with a maximum prefix length of a /21, and in addition, it will tell you in which tel it found it. So typically in a live production, you will see here RIPE-NCC or ARIN or AFRINIC or APNIC or LACNIC. All right. Now, let's have a quick walkthrough of the routinator, which is in our lab. So, sorry, where is it? It was here. So typically, where is our lab? This is our lab. Big shout out for Andre in the back of the room, because he's maintaining our labs. So that is the network diagram. So that is the environment in our lab here. We will be working on the validator, and later on we will work a little bit on router 1 to connect it to the validator. In our case, the validator is a routinator. So typically that would be the interface for it. Now, in our case, we only connected to one repository using the RRDP protocol. So it's a little bit limited. In order to do a walkthrough, we can use at the RIPE-NCC, we also have a routinator publicly available if you'd like to check it. So you can go to rpki-validator.ripe.net and you will land on an active RPKI validator. So you can have, at the very beginning, you can do a prefix check. So you can put a certain IP address and a certain ASN number, and you can verify if it's correct or not. So does anyone would like to volunteer and give us a prefix to check? No? Yes? Maybe? You'll have to speak a little bit louder. 193 dot? And that would be announced by which AS? 1213. When you click on validate. Oh, sorry. There's nothing for it? Okay, so you don't have. Let's see something else. All right, someone else. So you don't have ROAS for that. You do. Ah, all right, here it is. Okay. So usually it pops up, but now the. All right, so you do. And you also have an unmatched VRP, so that's fine. All right, so this is how you see in real time if you have ROAS out there and validated ROAS that matches a certain prefix. So, and it shows you how fresh the data is. So for example, it gets data from RPKI 1 minute ago, so the ROAS then validates them. It gets data from BGP 6 hours ago, and here it uses like the routing information services and so on. All right, and gets data from the RARs to see who is allocated the IP addresses, and that was fetched 5 hours ago. So basically, this is the prefix check. You can go to the metrics, and you can see here the different TALs. So from Afrinic, APNIC, ARIN, LACNIC, RIPE, you see the ROAs that were downloaded from the repositories there. You look at the, if you're interested in certificate revocation list, whatever the case is, how many valid certificate authorities there are, you can find the information there. So sometimes if you, and you can keep a tab on this. So let's say there's something bad that happens with one of the TELs, it becomes unavailable. It can raise some alarms. You see the numbers going down to zero. So that would, make you alert. You can check the repositories. So basically, these are the RPKI repositories where the ROAs are published in the first place. So some of them you can see that they are the ones from the RIPE, NCC itself, or or APNIC or AFRINIC, but there are some others. It could be maintained by other organizations as well. And here you'll find both RRDP and the RSync. So it would tell you each one of them, what are the status of them, how many ROAs there are, the total validated ROA payloads, etc. So if suddenly you start seeing an issue with one of these repositories, either you can isolate that issue or you can get in touch with them, you can raise some alarms, etc. And if you would like to see your active connections, you can find them here. So typically, this is where your validator at the very beginning uses the TALs to start connecting to the 5 trust anchors and the other places as well. So typically you'd see here the different RRDP connections that we have and the different RSync connections that we have, and give you some information about some stuff. So basically, this is what a routinator looks like. Of course, you have a command line where you can do some more troubleshooting. If you want to do some whitelisting or something similar to that, you can use it here. So that was our walkthrough. Now, how do you connect your router to your validator? Because at this point in time, you have your validator, you have your validated cache, so the validated ROAs. How do you push them to the router, right? And in fact, the validator doesn't push, so the validator waits for a router to connect to it and starts pulling it for the validated cache. So I'll give you two examples, one that we did over the Cisco iOS platform and the other one through FRR, and we'll do that in a live fashion. So all you have to do is you go into the router BGP config mode on Cisco's platform, and then you define there the RPKI server. So that refers to the validator software. And then you can you specify that it's a TCP connection. You should be having the IP addresses and the ports of these validators, and then how often do you want to go and ping these validators to download the data, right? Typically, after that, you wait a little bit, and then you can check the status of it using show IPBGP RPKI servers. It will tell you, yeah, we have two neighbors. So the first one, sorry, that's the first one over here. The connection is established. These are the ports that we're using. And then that's the second one. And that's the information. It's established. This is the port that I'm using, both to listen and to send. Now, if you'd like to see if your router managed to download the validated cache, you can use the command show IPBGP RPKI table, and then it would show you all the different VRPs. These are the validated ROAs, which basically it contains the network, the prefix, that's the prefix that we want, the maximum length information, the origin AS, and then the neighbor through which we acquire this information. And if you take a closer look, you'll see that for every network, we have two entries. So the first two are for the same prefix. The second two are for the same prefix. And the reason why is because we learn it once from the first validator and we learn it twice, or the second time, from the second validator. All right, and then you can give some sort of preference if you want. You can say, okay, I'll just use the first one, or I'll combine both the pieces of information together, right? So that is the how you can do it on Cisco platform. It's quite easy. Now for FRR, again, we're going to use our live network. And again, shout out to Andre. We're going to work on R1 to connect it to the validator, to that specific validator. Now, in our case, we only have, in this lab, we only have one validator. So we'll connect it to one validator. So this is the R1. So hopefully everything goes smoothly again. And the way you do it, you go in the config mode, you go into the RPKI config mode, and then you specify the polling period. Sorry. It's hard to type and look over there at the same time. So in that case, I specify the default value of 3600, and then I have to point it towards the RPKI cache server. So on Cisco, we point it towards an RPKI server. Here we point it to an RPKI connection, and we say it's 2001 DB8 30 30 FF, and then the port is 3323, and then I'm going to give it a preference of 1. Hopefully, if I haven't done any typo, I wait for just a couple of seconds, and then I do a show RPKI cache connection. And yeah, so it says I'm connected through TCP to this cache server. The preference is 1, and the status is connected. Now, if at this point in time, I don't have an indication if the router managed to download the ROAs. So in order to do that, I'll do a show RPKI prefix table. And yeah, in fact, it downloaded the ROAs. And it tells me, again, the same pieces of information, prefix, the prefix size, the maximum length, and the origin AS. All right. At the very end, it tells you some information about how many IPv4 or IPv6 prefixes that are included. So it is that simple. It's not rocket science. It's not very complicated. So now at this point in time, we have installed the software, the validator software. We managed to connect it to the trust anchors. We downloaded the ROAs, all of the ROAs. We validated the ROAs that are good, and we placed them into something that we call the validated cache. Then we managed to connect our routers to the validator. We downloaded the validated cache to the routers, and now they are available inside certain tables. Now, up until this point, nothing happened in terms of filtering. So one can argue that everything we've done, we didn't do anything in reality. So this is where BGP-OV comes in place. It had been defined in RFC 6811. And basically, it defines a framework that would allow us to drop or filter BGP announcements based on the BGP information. So the BGP announcements that I receive from my peers, from my neighbors, are now compared to the data in the valid ROAs. All right. The invalid ROAs, I don't take a look at them. I don't download them in the first place. So the origin AS and the maximum length must match for me to decide that the BGP announcement is correct. Right? So if I receive a BGP announcement for /24, but the ROA says I only validate up to /22, then no, it's not valid. Right? So how does the RPKI validate the origin? So let's say I have a router here, and we'll see the three different cases. My router in blue receives a BGP announcement from AS65500 for /48. It will go take a look at the ROAs, and it will say, all right, there is a ROA that says this /48 with a maximum length of /48 should be originated by this ASN. The information matches, so I'm going to put a tag, an RPKI status tag, which is called valid. Now, how does this translate in reality? If you go to your router, you put the show IPBGP and then for the route that you want or the prefix that you want, and you'll see that at some point there is a tag right now that says RPKI state valid. Okay. Now, what happens if I receive an announcement for, let's say, a /64? And typically, you should not be receiving in BGP something for /64. So typically, the most specific thing that you can receive is for /48. But let's suppose this is the case right now, and it's coming from AS65500. But the ROA says I only accept /48s, and the maximum length is /48. So in this case, the BGP announcement would be marked as invalid, and the reason why it's invalid because the maximum length doesn't match. Or it could be the case that I'm receiving an update for a BGP update message for the /48, but this time it's coming from a different AS, 65400. So that one will also be marked as invalid because the ROA says it should be 65500. Now, there is no issue in having different ROAs, one ROA for this and one ROA for that. But specifically in this case, we only have one ROA that validates the origin announcement. So that one would be marked as invalid. Just by the way, when we did the previous check with our colleagues' IP address in the back, we saw that that announcement was valid according to one VRP, but invalid according to another VRP. Now, the status in this case would be state invalid. And in our specific lab scenario, the reason why is that this /24 was being announced by another AS, and that's why it's invalid. Now, it could be the case, and by the way, that's true for almost 45% of the traffic, or 50% depending on the region we're looking at, that we receive a certain announcements. So in this case, for this /48, but we don't have data and ROAs against which we can compare the information. So the status in that case would be marked as not found, and the tag, the RPKI state would be not found. All right. Now, okay. So how do we decide on this? How does the router decide if it's valid, invalid, or not found? Well, it goes through this very specific, very simple algorithm. First, if there's a ROA that exists that validates the prefix is valid. So at least we need one ROA to validate it. Then, if there are no ROAs that validates, but there's at least any ROA, so at least one ROA that invalidates the prefix, either because of wrong origin, wrong ASN, or a maximum prefix length mismatch, then the prefix would be marked as invalid. And then the final step, if either or we couldn't find something that validates or we couldn't find something that invalidates, it will be marked as not found. So basically, this is how you can, this is how the router can use the data from the validated ROAs to mark the BGP announcements as either valid, invalid, or not found. Now, if you'd like to check it, I already showed you the outputs, but we can do that if you want here live. So in my case here, I'm using user 29, all right? So what I want to do is I want to start announcing in BGP the prefixes of user 30 in our lab. So, and then I want to check the status of it. I tried it twice yesterday in the evening, it worked, so fingers crossed. But the rules of the demos are if something can go wrong, it will go wrong. So let's hope not. So I'm going to be announcing, as I said, a /30. If I get my, okay. Because I'm not using this specific prefix in my network, I have to add a static route for it because otherwise BGP will not allow the announcement of a prefix that doesn't have a route towards. So in this case, I created the static routes, and then I go into my router BGP mode, router BGP 200. I go into address, family, IPv6, and then I start announcing this network. So it's 2001, DB8, 3000. Oh, okay. Then I wait a couple of seconds and I start praying or what have you. I look at the show BGP. And now, because I managed to connect this router to an RPKI validator and downloaded the VRPs, now when I look at the BGP routes that I'm receiving, it will tag them with either N for not found or invalid I, so that's an invalid, or the valid. So in my case, I'm user 29, so I should be announcing this 2900/48. So theoretically, I should be seeing, here it is, the 3000/48, which is typically, it should be announced by user 30, but I'm user 29. So this is marked as invalid. So if I do this, if I take it here, hold on, copy, and I go to the validator here, and I say this being announced by yes 33,000, and I validate, it should tell me no order, no. Oh, what happened? Ah, hold on. Okay, so it tells me that this 3000 should be announced by ASN 3000, which is for user 30. But in my case, I was announcing it from AS29, and if I validate it, it says that there is an unmatched VRP. So it says that according to the data and the ROAs, what you are announcing is invalid, and the reason why it's invalid AS. All right. Now it could be invalid ASN, but for prefix lengths, but that's not the case here. All right. Now, going back, we could be in a scenario where we say, all right, we might need some local overrides. So what if one of my customers did something bad, a misconfiguration, right? Or they started announcing a prefix that is invalid, or whatever the case is. And I stopped dropping these announcements because they contradict with something in the ROAS that they had created before. I have two options here. Either I can disable the whole filtering based on BGP, based on RPKI data, but that's not a good thing. Or we can ask the customer, in that case, to create the proper ROAS and wait. It might take, I don't know, half an hour for them to do that, and then for my validator to download the data and push it to the router, etc. Or I can locally do an override, right? So sometimes there is this operational need where I need to create local ROAS on my validator software on a temporary base to allow a certain announcements. And then there's RC 8416 that defined a certain framework for the certain format for it called Slurm. So using Slurm, you see here at the very left, it says, I would like just on my piece of validator to introduce a ROA that validates a /24, this specific /24. And that could be on a temporary basis until the customer, get their act together. They create their own ROA, they publish it, I get it, and then, I continue with it. Now, the recommendation is use it with care because you're introducing temporary exceptions. But these exceptions, if you don't revert them back, they become permanent, not on a temporary basis. Now, the thing is, with everything that we've done so far, we still did not do anything in terms of security. So all these tags that we saw, the invalid, the valid, not found, it means nothing. It's just a tag that we put on the router, on the root. The router will not take an action. So the invalids, they are not dropped. We just mark them as invalid. Might as well call them blue, green, yellow, etc. What we need to do next is that we need to inform the routers what to do based on these RPKI statuses. So typically, if there's a valid route, you should accept it. You should accept the prefix. If there's an invalid prefix, you drop the BGP message. You drop the route. You don't accept it. Now, if there is one that is marked as not found, chances are you need to accept it because that's around 45% of the routes on the internet. Now, if you decided you woke up in the morning and you chose violence and you say you want to drop them, you can. But I'm not saying that you should do that, please. All right. So the recommendation out there is that do not consider dropping prefixes, especially the not found, based on the RPKI validation state. Now, if a few years down the road we have 99% of the routes as valid, you can say, you know what, I'll take my chances and I'll drop both the invalids and the not found. Now, how do you do that? Basically, it differs from one platform to another. But in our labs, for example, either on the Cisco platform or the FRR, it's very similar. You have to configure a certain route map. So you have to configure your validation policy. You have to tell the router what it does. So you can do one of two things. Either you can say, that's the first approach. So you match the valids. So the RPKI valid routes, you match them. And you say, you know what, for those, not only I'm going to accept them, but I will boost the local preference. I put the local preferences in yellow because you don't have to do that. But if you want to, you can do that. So you put the set local preference to 110. And then for another policy that says if you match a not found, so if the RPKI status is not found, then you permit it, but the local preference would be you lower the local preference. And that's it. That could be your policy. Why? Because there's an implicit deny. So if you only specify what you want to accept, you deny everything else. In other terms, the invalids would be dropped. Now, we can add a third policy that says route map, RPKI accept, deny 30 or whatever, and then we patch it on RPKI status invalid. We can do that. All right, and then we take this route map and we apply it to our neighbor in the inbound direction. As simple as that. And from now on, going back to my case where I'm doing peering with Andre. So let's say Andre is this neighbor. He's sending BBGP announcements. I run them against this route map. If what Andre is sending me and BGP announcements is valid, I accept it. I boost the local preference for it. If it's not found, so I don't have a validated ROA for it, I accept it, but I lower the preferences. And if it's invalid, you know what, I just drop the whole thing. Now, there are major networks out there today that are doing the RPKI validation, they drop the invalids. These can be, sorry, they can either be tier one operators, they can be cloud providers, hosting providers, big service providers, you name it, everybody is doing it these days. And according to them, they follow the phase approach. So first they started with their peers before rolling it to the customers. At the end of the day, you don't want to start testing stuff with your customers who are paying you, you know. So what they did is that they started tagging the invalids for all their peers and then for all their customers, and then they started dropping the invalids for the peer and then for all their customers. Now, it really depends on your operational need, how you do it. So, for example, I told you about the engagements that we're doing in the Middle East with the operators there. And one of the approaches that we're using, that we're doing, for example, now in Saudi Arabia, is that we're working with the operators for a period of 2 months, where they will run their validators, start tagging the routes, either valids and invalids, do the logging, do the analysis, and then at the end of the 2 months where they are sure that dropping the invalids will not affect any of their live traffic, this is where we'll start actually dropping the traffic. Now, either you can take this approach if you want to be cautious, or you can say, you know what, I'm pretty sure that my peering sessions, everything is correct, so I'll start dropping the invalids right away, and then if something breaks, someone starts complaining, then we will fix it accordingly, right? Now, from a statistical point of view, how safe is it to, like, if we start doing the validation, how much of the IP space can we cover? So from a global perspective, this year we crossed the 50% boundary. So what it means is that more than half of the IPv4 space in the world, at least the associations between the IP and the ASN in BGP, are valid. All right, a little bit less than 50%, the yellow here, are still not found. And that's why we're saying that do not drop the not found. That's almost half of the IPv4 traffic. And then you see the invalids historically, they are very, very, very low. So you can just drop them, right? It will not affect. This will be noise, peanuts, right? I was giving one time this workshop in London. There was one guy, I think he's more pessimistic than I am. And he said, oh, the invalids are, they grew at some point in time a little bit, but it's still peanuts, right? So that's IPv4. IPv6, it's even better. So we actually crossed the 50% mark in the validation space, almost a little bit like early 2023, so almost a year before we did that in IPv4. So moral of the story, do IPv6, please, right? That's on the global scene. So what does it look like in the RIPE region? Things are better in the RIPE region. So typically today we sit at around 70% of the IPv4 space. So the mapping between IPv4 and ASN in the RIPE region is valid according to ROAS. So according to predictions, maybe in the next couple of years, we'll be hitting the 90% mark or even more. And for the IPv6 space, it's even better. So in the IPv6 space, we're flirting with almost 80% of, the pairs between IPv6 and ASNs are valid. So we're definitely on the right track, right? But these statistics are for the IP address space that is being covered by ROAS. Now, the next pieces of statistics, and these are provided by our sister organization, APNIC. Now, I have to say, this is not 100% accurate, but it gives you a good understanding or a good indication of whether the networks are doing validation based on RPKI data. So the greener the country is, it means the users there are more or less protected by RPKI. It means their service provider or someone along the upstreams, a certain network along the upstreams, are filtering routes based on BGP data. So you see that there's a lot of work to be done. If we focus a little bit more on Europe, you see that some countries are doing better than others. We currently at the RIPE NCC, we have several programs in Central Asia, in East Europe and in the Middle East to try to push for the phase 2, we call it phase 2, which is the validation. All right. So, in a nutshell, RPKI is a very powerful mechanism. It prevents the BGP hijacks, specifically the misoriginations and route leaks. It still does not protect against the attacks on or the incidents on the path itself. It is a stepping stone, and we'll see that in a second. Now, RPKI, as you might already know, is opt-in, so it's not enabled by default. So please, if you haven't started yet, please do so. So let's deploy RPKI. That's a call for action to get you all emotional and started. But yeah. Now, I'll finish the workshop with a little bit of what are the next steps today in the BGP routing security. So we dealt with the BGP origin hijacks through RPKI. Now we need to start dealing with the path hijacks. And the path hijacks can be one of two things. Either I can fake a path. So in that case, you see the adversary here, AS5, sending to AS4 an announcement that says, yeah, you know what, I have access, I don't have the prefix /32 itself, but I have a direct connection to AS1. So send me your traffic, right? I'm very well connected with that. But this one doesn't exist. So AS5 doesn't have a link to AS1. So this is what we talk about a forged AS link. Or it could be the case that I don't forge an AS, a link, but I change the path. So let's say this is the case here, that AS1 is sending BGP announcements. It sends it to AS2, AS6, it goes to AS3, it goes to AS5. Now AS5 is malicious. It wants to hijack the path going towards AS1. So what it does is that it sends the BGP announcements, but instead of putting AS6 in the path between AS5 and AS1, it says, you know what, I'm directly connected to AS1. So it's not that AS5 cannot get the traffic to AS1. It does have a route to it, but in reality, it changes the AS path. All right. So these are two ways of targeting the path itself. Either I can create a link that doesn't really exist and tell you, yeah, I'm connected to Meta, send me your traffic. Or there might be a path between me and, I don't know, Andre, but there's 3 different ASs in between. And I can say, you know what, yeah, I'm directly connected to Andre. My routes are optimized towards him. Please send me your traffic towards Andre. Okay. So today, RPKI focuses on the origin validation. Now, what we need, the next step is that we need to validate the full BGP path. So from me to Andre, there should be a way to be able to validate every single step in the path or the attributes as well between me and Andre. So there are 2 tentative solutions for that. One of them is BGP SEC, and the other one is ASPA. They both use RPKI to get there. So let's discuss them very, very quickly and briefly. The first one is BGP SEC. It is designed to supplement the BGP origin validation. So it also relies on RPKI certificates. Guess what? It has security in the name, so it will be using cryptography and certificates to verify every single connection in the path, and not only between ASs, but between the routers themselves as well. So it introduces a new BGP path attribute called BGP-SAC_path. It's optional, non-transitive attribute. What does it mean? It means if there are 10 routers between me and Andre in the back of the room, and one of the routers along the way doesn't do BGP-SAC, then in this case it just drops the BGP-SAC information and the traffic the BGP messages go naturally. But that also means that if I want to have BGP-SAC between me and Andre, all the routers between me and Andre must do BGP-SACs, right? It carries digitally signed AS path information, and the support is negotiated between the BGP speakers. So at the very beginning, when we're opening the BGP session, we send the BGP open message. There's the capabilities exchange, and this is when we negotiate if we can do BGP-SAC or not. If both of us do BGP-SAC, then we start using it. If not, we don't use it, as simple as that. So what happens in this case is that the routers are going to sign the AS path in the BGP update message. So not only do we send the AS path, but we will sign it. We will put ourselves in the path and we're going to sign it. So each BGP update message will contain a BGP SEC path attribute that says a specific prefix and can only be sent to one AS at a time. So if I have, I don't know, I'm announcing 100 different BGP routes, I will do it 100 times, right? And there's no optimization here. So that's why BGP-SAC is a little bit heavy, right? And what it does, that every router that does BGP-SAC, it will have to verify the whole chain for every single BGP update message that it receives. So it would look something like this. The first the first router over here receives a certain BGP message. It verifies everything, and then it will put itself in the AS path, and then it is going to sign it with BGP-SEC attribute. It will have a pointer to the public key, where you can find it in the RPKI certificates, and then it will sign it and will include the signature. It will send it to network 2. Network 2 will look at this. It will verify if it is correct. If everything is correct, it will put itself in the network in the AS path. So now the AS path is network 2, network 1, and whatever the case is, and then it will sign this, and then it will add its own signature and the key, the pointer towards its public key. It will send it to to network 3. Network 3 will go verify the signature of network 2. So it will verify that this is correct, and then it will verify that this is correct, and then it will verify that this is correct, and then it will add its own signatures, own key, and sends it forward. What I'm saying is that if there's 10 routers between me and Andre in the back of the room, all of this should be done at every router for every prefix. And it's not only that we're signing the prefix, we're signing that specific connection between this router and that router. So if I have this network 3 peering with 3 different routers from network 2, it's going to have to do that 3 times. So it's quite heavy. And that's probably one of the reasons why BGP-SAC wasn't adopted completely, even though there's mature implementations for it, mature stacks. It's an RFC standardized. But realistically speaking, it's heavy. And it does not support incremental deployment because, as you saw, every router will have to verify everything before it, and then add itself to the BGP-SAC path. Let's say I send this to network 4. There's a router here that doesn't do BGP-SAC. All of this would be lost. So network 4 will remove everything and then just send it plain out to network 5, and everything got lost. So if we need to deployment, it should be all the way from between here and the back of the room. We cannot do incremental deployment. Now, ASPA is the other approach. It's called Autonomous System Provider Authorization, where basically it introduces a digitally signed objects that probably could be published in the RPKI repositories, where me as a network or whatever, as an autonomous system, I can specify who are my upstream providers, right? So who is allowed to carry my announcements to the internet and so on. Again, it leveraged the existing RPKI infrastructure. It doesn't require a change in BGP itself because we're not doing computational stuff on the BGP messages themselves. It's just that if let's say Andre receives a BGP message related to my IP addresses, saying that it went through Xavier as my upstream provider, Andre can check if Xavier is really my upstream provider. So if we go back to this specific scenario here, and we have AS5, and we see AS5 announcing to AS4 that, yeah, you know what, if you would like to send your traffic to prefix 32, I'm directly connected to AS1. So in other terms, I might be their upstream, so send me your traffic. AS4 can go look at the RPKI data and see that, hey, AS1, they specifically created an object that says that their upstream providers or whatever are AS2 and AS6. So in other terms, in the AS path, you shouldn't see AS1 and then AS5 directly after it. So you should see AS1, AS2, or AS1, AS6, etc. And the idea is that if each one of these ASs does this, then we would be in a scenario where more or less we can verify that the AS path looks legitimate. So that's the idea behind ASPA. All right. So yeah, I explained it quickly. Now there was also work around something called AS cones, where basically we do the same thing, but instead of specifying the upstream, we specify also our customers. So basically, who we are acting as an upstream for them. Right. So ASPA allows for incremental deployments. So because again, we're not doing computational stuff on the BGP messages, it is still in a draft state. Hopefully soon it becomes an RFC, and there are some support already in some of the implementations out there. And with this, I get to the end of today's tutorial. If you'd like to know more and get your hands dirty on BGP, I can refer you to the BGP Security e-learning course. It is available on our Academy platform, so you can go to academy.tribe.net. These courses are completely free, self-paced. They are modular, so if you're interested in one topic but not the other, you can do that. The exchange, the knowledge experience is interactive. So there's videos, text, labs, hands-on labs. You download them, you run them on your own machines. Again, a shout out to Andre for helping setting up the labs environment. All right. And if you feel that you're up for a challenge and you'd like to be certified, you can check our certified professional services at getcertified.tribe.net. We currently have 4 certifications. One of them relates to BGP security. These are not easy exams, but they are not hard either. So it's just the right amount of challenge. But if you go through our academic process, if you follow the information that we share in the learning blueprint that we provide, you should be okay. Yeah, and with this, I get to the end of a tutorial today. 9 minutes in advance, and that's a first. Thank you all for joining on Monday morning. If you have any questions, please feel free. Thank you. Questions? No? Either I'm a very good trainer, which I know I am, or you guys are sleepy, or both at the same time. But if there are no questions, I hereby relieve you for some early coffee. Enjoy the right meeting, everyone.